My name's Ram. I'm a PhD student here at UC Santa Barbara. I work with Alban Soure, but he's since moved to Maryland. I was not going to leave this beautiful weather. It's been a while. I'm a fifth-year student already, so I'm going to try and summarize a bunch of work that we've done over the last few years. Will not be able to do it in as much detail as I would like, so I would love it if more of you are interested in any of this stuff. Please come find me and we'll talk some more. So confinement is quite normal in natural and industrial systems. We just saw a great example before this. In some cases, we don't want confinement. In some cases, we want confinement. So here are a few examples. Human-made infrastructure sometimes confines flows quite naturally. Storm drains, you can think of other stuff like this. Sometimes we want to actually stop a debris flow. That's the second image that is up there. Whereas this group, based out of Hong Kong, uses these really dense nets to try and stop debris flows from spreading. In our group, we've been quite interested in clogging for a while, so that third picture is from one of many works from Alban. New reviews upcoming in PhysRev Fluids soon. Yes, Alban? Please have a look at it. And then he's done a great job of summarizing clogging in a bunch of different systems. So if you're interested in clogging. For today, we're going to focus on really this last version of the problem, which is an hourglass. It's a pretty simple classic problem, but in my mind, there are lots of problems within the hourglass that we don't actually know well. I'm looking for a dry spot. There's somebody. Oh, yeah, I'm just going to start. It's okay. Sorry about the drawing. You can imagine there's a bunch of confinement happening in a few different spots in here, and we're going to focus on some of these. So one question is, what happens with confinement and stresses far away from the opening? There are really two problems that we are interested in quite close to the aperture. One is kind of confinement and flux, which is what we will talk about today mainly. But again, clogging is an interesting problem, and maybe if time permits, we can say a little bit about clogging as well. We also know that once these grains fall, and once they are free from confinement, they kind of look like they're thinning. So you have something here in the middle where as soon as you kill confinement, even though the system is not at all a continuous system, you will get something which looks like it's thinning. And maybe we will try and answer, why is a kinematic jet thinning? Is there a ballistic reason? And then you've also seen at the base of the hourglass, you'll have a nice pile. And so one last question is, when you put a rigid surface at the base of a pile like this, under what conditions do you pile? Under what conditions do you spread? And we will try and answer a bunch of these problems. Today, maybe we'll just focus on the silo, which is maybe the easiest way to start. So we will focus on the flux to start off. Let's go here. The reason we use hourglasses, and then there's a cheap hourglass which is circulating here, which kind of gives you about 3 minutes of time. We use hourglasses really because they measure durations of time well. The speed at which material kind of drains through this little aperture is fixed. It does not depend on the height of grains that remain in the system. And just to give you an example, here's an experiment. You'll see me show up an MTR silo, just to give you some idea of what kind of experiments we do here. Historically, there are a few approaches. The oldest one is actually from Hagen, which is kind of an old approach. So this is an 1852 scaling analysis, where we figured out, quite truly, that the density of grains shows up, gravity is important, the size of the opening is important. This is kilograms per second, which is kind of mainly going to be what we are interested in today, a flux, really a mass flux. This is just the density of the grains, gravity, and this is the size of the aperture. So in Hagen's original analysis, there's no effects of confinement. It's the simplest version of the picture. Okay, in the 1960s, sorry, Beverloo, and there's a few different approaches, essentially put in a scaling constant right at the start here, where we introduce a new parameter, which I will talk about in 1 second. And then we add a small other fudge factor for the effects of confinement. So if you just do the scaling analysis, it turns out there are a few pieces you're missing. If you think about spheres, they don't occupy volume fully. So you need to account for some amount of how the volume is being covered in the system. And in the old analysis of Beverloo, these guys together define what we call a bulk density, where you have the density of the grains and how well they pack space. We introduce a constant, and of course you do lots of experiments to figure out what something like this looks like. And a bunch of experiments since this paper have shown that this number kind of lives somewhere there. And then, unfortunately, just this also slightly overpredicts the flux. So you have an effective size, which is essentially the effects of confinement in the system. And for this, we put in a constant K, which is about 1 to 3. That's where usually people are. Since then, okay, last one, I promise. So in the 2000s to the 2010s, Iker Zuriguel and the group in Spain have done a lot of cool work to extend this. And what we can add here are a few more pieces in terms of what they've done. Still have C from Beverly. Okay, I'll explain in 1 second. But we're not done. It's a big equation. Okay, so here's a new expression that we have from the 2000s. Again, we keep the same C in this picture. We kind of fix K equals 1. Also in this picture, that's where the second constant lives in there. And what they find is actually you have some kind of an exponential correction which shows up because of confinement. If you make the system bigger and bigger at some point, the variation stops. But to explain this, they unfortunately have to put in 2 more constants, which are essentially from empirical space. So this B here is 0.051. It's a really small quantity. Yes?
You've mentioned the word confinement already.
Yeah.
Which is important.
Yeah.
So I'm just curious. I always thought that if the walls are horizontal, then it's constant flow rate. As soon as you get to the ends, like bits,
yeah,
then you might have some adjustments. Is that in that last equation?
That's the point. So that is precisely, for the purposes of today's talk, what I will call confinement. Right at the edge, what the edge is doing. Mm-hmm. All right. Yes?
Justin Burton
had
a talk in the conference discussing the gas flux, I guess.
Yeah.
Is this included in the scalar?
This is not. So that's a great point. So actually, if you look at the hourglass, the one that is being passed around as well, it's slowly going to be jittering as air is trying to go upwards. We try and solve this problem in silos normally, but also for us in the lab by keeping everything open. So if everything stays open, we don't have to really worry about air. Yeah. And of course, the glass beads are much, much heavier than air. Yeah, okay.
Do things like surface roughness of the particles and so on, does that mostly enter into this constant C?
Yeah, that's what we think. It also enters here in terms of like over what length is the system actually being confined in terms of grain diameters. But these are precisely the questions which, unfortunately, such relationships keep a little unclear. And so maybe we'll get into the heart of this today. I think we're going to start fresh. So we're going to kind of let all this go and start with a simple approach from scratch. Just to give you some examples. So if you consider really large grains, these are about 4 mm grains. And the opening is about 5 mm, so they're equal sized. You get clogs. The system will never flow. Even if you make it about 2 times the size of the grain, you still get no flow. If you make it a little bit larger, you start having some flow, a little bit like a dilute flow. And we will collect the grains as they fall. And what I'm plotting below is just mass as a function of time. The slope of this line gives us the flux. All right, you can consider a bigger opening size. You can see the jet already looks like it's getting denser. And we do a bunch of these mass flux measurements as a function of opening size. And these are these blue triangles. I'm going to keep the opening size the same, but just scan through a bunch of grain sizes. So if you half the grains, so these are 2 mm grains now, still the smallest one is clogged. The other 3 start flowing. You can already see that at the big jet, you kind of have a nice dense flow developing. What we can also see is that the flux here looks larger than what it does for the bigger grains. So clearly grain size is affecting flux. In fact, if you see on that big plot, you can see the purple data always sits above the blue data, generally speaking. Half again, this is about 1 mm grains. And now you can see flows everywhere. And now you can maybe more clearly see the dense jets when the grains are much smaller than the aperture. Again, flux is getting larger, but now you can see as we make the opening larger and larger, at some point, the flux stops depending on the grain size. We'll do 2 more, so this is 0.5 mm, and then this is the smallest one we'll probably do today, which is 0.25 mm. At this scale, we still don't have to worry about van der Waals. Air can still have very minimal effect at the size of the grain, which is kind of why we stop here. We're not going to go any smaller than this. All right. We can see a few things already, and I'm just going to summarize what we are seeing here. If we look at all these jets, when the opening is much larger than the size of the grain, you get a nice dense jet. So it looks like we are approaching some kind of an asymptotic state. And we're going to start by considering what that state may be. So in the limit that the aperture is much larger than the grain size, we get a simple idea. This is always true, but I'll simplify it in 1 second. We are interested in area, some idea of the density of the grains. We want to know what's happening to the packing over the aperture and what's happening to the gravity-driven velocity over the aperture. Right? This is generally how we are interested in the flux. It will depend on the area. The bigger area will give you a larger flux. And what we really want to know is kind of what's happening to these two pieces, which essentially make up the distribution. Packing, velocity. These are our two main ingredients. You can imagine if you consider this limit, so when the opening is much larger than the size of the grain, this system is broadly ballistic. So you might expect, even naively, that the velocity should just depend on the size of the aperture. And so let me just show you. Okay, and to do this, we start doing some simulations. Alex is involved. Of course, Alex, you can just speak in the middle if you want to. Okay, let's start with the velocity. And as you see for a range of simulations, as we make the aperture size larger and larger compared to the size of the grain, essentially the system saturates at very expected this value. This is what is interesting. Okay. The other piece is packing, and packing is a little less obvious. What's happening to packing? What happens to packing in free fall? Not clear, but we can assume that this is what's happening to the velocity. And from a bunch of our experiments already, using mass conservation, we can estimate what's happening to the packing. And from the experiments, packing in free fall kind of saturates at about 0.54. And if we do this in simulations, we get these nice plug-like distributions. The yellow color here is a small opening size, the brown is a large opening size. For all of them very close to the boundary, you have some modification due to the boundary. But far away, you get this nice plug-like shape. Here as well, even in our simulations, this number is about 0.56. So for us, we usually now expect this to be about 0.55. And for many of you here who are familiar with grains, this is not a surprising expectation, but let me just give you a little bit of the physics. Essentially what's happening is a bunch of grains which are rigid at some packing are going through a de-rigidification as they fall through the system. And we get a packing which corresponds to the minimum random loose packing of the system, because this is the smallest packing you can have while maintaining contacts, but no loads, which is what's happening. Yeah?
Presumably this entire thing is very sensitive to the inelasticity coefficient of restitution, right?
Yes.
Because in the limit of no restitution,
Yeah.
the ideal gas at that point,
Yeah.
then you will not have.
You will not have this. So this is why we start with glass beads. It's a nice one where you can assume very, very hard systems. So far, and I mean, we'll show you also how this framework is developing. It's purely geometric. So as long as you have spheres, we can assume they don't really deform much. This is quite okay. Anything else? I'm going quite fast, so I can also slow down as you guys wish. All right, we can keep going. Okay, and let's decide a quick comparison now. So we have, using this, some estimate of how does this system flow when it's actually freely flowing. And we said this will depend on the area and density of the grains. We said that the packing will go to some free fall packing, which for us we said is about 0.55. And then we said the velocity is only going to depend on gravity and some transport length scale associated with the size of the aperture. And that's all you need. So now you have some expression of flux only when the aperture is much, much larger than the grain size. We can compare this with the rest of our data by just considering a simple fraction. We call this f, because I'll connect it to a fruit number in 1 second, where we take the measured fluxes that we have and just compare them with the free fall flux. This is what I'm plotting on the left-hand side of this screen here. So as you can see, when the two scales are similar, when the size of the aperture, size of the grains are approximately equal to each other, this ratio is essentially what goes to 0. So f essentially for us will live between 0 and 1. And at 1, essentially gravity is going to give us what we want. And at 0, essentially confinement, the way we are talking about it, dominates what's happening. All right, so for smallest grains, you can see this already, but I'm just going to put a bunch of data on it, just so you can see that across grain sizes, the effects of confinement are the same. Where is this coming from? And we will talk about this in detail in a few more seconds, but if we look at the packing profiles, if I try and plot what is happening to the packing at some radius, close to the wall we said that the packing has to change a lot. Far away it's kind of plateaued to some value. So we get a nice plug-like shape there. What I'm showing you in this plot is instead of plotting it in these radial coordinates, we are just looking from the wall. That's all that's happening. So as I keep changing the size of the aperture, if I change the size of the grains, they all still follow in the same curve. This is what is essentially some kind of a packing boundary layer. It is where packing is being greatly modified in the system, and beyond which the system starts flowing freely. We can think of this as a simple one-parameter exponential, which is kind of what you can think of here, because there are two distributions which are evolving, and this kind of just forces them to be one. Of course, in reality, both these distributions are going to be relaxing to some asymptotic value. So if you really want to get into the details on this, we will have some relaxation from packing, which comes from this boundary layer, which is essentially what dominates this exponential for us. And then you have a much slower relaxation as the velocity reaches like a free fall velocity. A stretched exponential just puts those both in one equation. That's it. All right, and that gives us a new expression for the flux, where besides everything that you needed for free fall, we introduce the parameter f, which goes from 0 to 1. And that just tells you exactly how the effects of confinement lay in this system. All right, anything else? Oh yes, okay, it's the Froude number approach. So this guy that we define as the ratio between what the measured flux is and the free fall flux is essentially a Froude number with the addition of some way to estimate how masses are changing. So you can think that this is the actual measured estimates, whereas in the denominator we just have what would happen in free fall. If you just think of this half of this equation, that's exactly how we define a Froude number in fluids as well. We have to introduce a new term to account for mass distributions here. So it's like a Froude number. And this kind of governs the structure of the jet, besides the relative aperture size compared to grain size. All right, this work has recently been accepted in PRL, and I forgot to add the QR code, but it'll hopefully be out soon. We're working on the proofs. One last piece that I think I want to talk about, and then we go into detail on what's happening. This packing profile is essentially, across our data, kind of like a first-order relaxation equation. So very close to the boundary, what's happening? Spheres cannot pack very close to a rigid boundary. So essentially, the closest a center can get to a boundary is one sphere radius. And this always ensures, people have shown this for many static cases using DEM, etc., that you will always have some kind of an exclusion principle at the boundary, which is super important. And that's precisely what's showing up here. And if you integrate this exclusion principle over the entire aperture, that's what's on the other plot, where you're looking at a mean packing of the system. And that's what we observe. This is the slow relaxation of packing. All right, so this was the first work. Very simple, circular apertures, spherical particles. It's as simple as the geometry gets. We're working on a number of daughter projects. What happens if you put a little bit of stickiness? So as soon as you put some stickiness between grains, this jet starts breaking up. Here's an example of that. If you change the size of, or the shape of the grains, we did sizes already, sorry. You can see, for instance, some rice on the top left, and rice likes to stretch in one direction. So now when this jet comes out, there is a preferred orientation of the grains. So this is one piece we are still working on, what happens with particle shape. Yeah?
Is it me, or is the rice that you mentioned kind of expanding in width as well? Because if you look at the left of the general framework,
Yeah.
the jet diameter seems to be constant. The rice just kind of seems to spread out.
Yeah, it really depends on the relative size of the grain and the aperture, and I'll go into this in one sec. If the aperture is much larger than the grain, geometry dominates, the jet will always thin. If you come to a limit where those two get similar, the jet stops thinning, it's more or less equal sized. And if you come to the other limit where they're maybe very close to 1, then the jet starts actually expanding. This changes with grain shape. And we are not 100% sure about this, but I'd love to talk some more. On the side next to the rice is some crushed glass. So these are some sharp grains, and there's a much bigger distribution of grains In this case, it's a little harder to estimate what is a loose packing of the system, to estimate what it would be in free fall. And this is maybe closer to what the industry deals with. Yeah?
I can't help to but notice that the 055, if you take less beads, and you freeze them, and then you just let it defreeze, that's typically the concentration you get, despite the fact that the random close packing is 0.6 for glass beads usually. Right? You get a value that is pretty much that. So I was wondering if you could use just freezation experiments to predict.
Oh, it's true. We should.
I'm surprised if it doesn't work.
Yeah, it's true. We should actually do this. This is a great idea. I'm going to write it down as well. But yeah, in that limit, exactly, the grains jam at the smallest packing, which is exactly what we need. Perfect. Yeah, thank you. Anything else? Lila?
I think when you, just to answer Marcel's question, I think when you have particles that are not equiaxed, that is, if they have a aspect ratio like that, the moment they start depositing, they'll always deposit to the long axis orthogonal to gravity.
Deposit. So you're saying right at the aperture or like some distance below?
The particles are, I think, turning.
Yep.
As you move towards, as they hit the file.
Yep.
They rotate and the particles deposit orthogonal, the long axis orthogonal to gravity.
It's not always the case for us. I'll show you some piles. I don't have piles with the rice here. For us, it's not always the case that they are that way. Once the jet is in kind of free fall, you can imagine one grain is kind of just in ballistic motion. So if it starts with some rotation, it's going to continue processing with that rotation. That's all we see. There isn't a clear way just through gravity that the grains have to be one way. I mean, I think when other grains get involved, then the question is, yes, near boundaries you will have some flattening. Yeah. Is that a hand, Sriram?
No.
No. Okay. Anything else? We're doing okay on time. Okay. No, it's good. We can keep going.
Slower.
Yeah. Oh, but it's fine. This is. I think you guys understand this problem already quite well. So it's just we can go fast. The two pieces of this that maybe I will take maybe one more slide on is what cohesion does, and what happens if the aperture is not perfectly circular. So you can imagine if there is a sharp corner in the aperture, this is going to change how packing behaves. And then in the future, we are looking at inclined containers and what happens if you just have a hole on the side of a silo, you still get a constant mass flux. And if we can use this to estimate the stresses inside the column, which we can. And then the work on the right is a new PhD student of Albans in Maryland, who's now working on suspension flows in 2D that we can actually see all the grains and track them as well. All right, so cohesion, or some interparticle adhesion for us, essentially breaks these jets up. So what we are looking at is about 20 centimeters below the aperture. So we are not looking right at the aperture anymore. And what you can see is as I make the size of the aperture bigger, all this is just 1 millimeter grains, slightly wetted with water, 0.5% of water overall. That's it. You can already see a pretty big shift in how this jet behaves. Besides the variation of packing in the radial direction, we've introduced the variation of packing in the z direction as well. And this means that if you now consider these plots to say, okay, how is this jet doing compared to free fall? It relaxes much more slowly. So that's kind of what you see as we look at all the blue data points here. These have been made cohesive with a small amount of water. The green data points have been made cohesive with a small amount of mineral oil. You can imagine as this jet is falling, we were a little worried how relevant is evaporation. Turns out not very relevant. And the last one is this polymer coated grains of Adrian guns, if you guys are familiar, where you can apply a polymer coating based on the thickness of the coating, you can control how sticky the grains are. So these are a few different sources of cohesion. Broadly, live in the same framework. To measure the actual bond number, which is a very useful quantity when we are talking about adhesion, it's just a ratio of the adhesive force between two grains and the weight of one of those two grains. Sriram has made this setup. Sriram was sitting in the back also in our lab. Has made this amazing setup to actually measure the forces between two grains. And so what we are plotting on this x-axis here in the inset is exactly this quantity. How sticky is it? And on the other quantity, what we are plotting is that you need a much larger aperture to start having any flows with cohesion. Essentially, cohesion is balancing gravity up to some limit, which is why those two actually behave reasonably 1:1, because essentially what you have to do is break all those bridges for this jet to actually separate. All right, recently Alban and I have written a review on how do you make grains sticky. for lab experiments, so in case you guys are interested, that's another nice place to look. All right, two other aperture shapes, just to give you some idea. So on what you're looking at for the videos is a 2:1 rectangle, and you're looking the long axis and the small axis. Just to give you some idea that on both axes, this jet is now thinning. What I'm showing you on the inside is you have to change the transport length when the circle is no longer, when the aperture is no longer circular. And that's what we are showing here. If you think of a generalized radius, you get a pretty good understanding like this. It does look like, as we change the aperture shape, the system relaxes more slowly to the asymptotic value. Just to give you some idea as to why that's happening. So here are some DEM simulations of the same. What you're looking at on the top is the average packing fraction, right at the aperture, so this is averaged in time. And you can see a little bit of the boundary layers already, but if I just plot the contours on top of this, maybe it'll become even more clear. That very close to the boundary, you actually develop a very similar boundary layer, in this case as well. Whereas the velocity plots, which are the ones which are in the bottom, are essentially diffusing a little bit more slowly into the system. So if you just cut a straight line to ask what's happening at the wall versus at the apex, just to give you some idea. On the top, you can see that the packing very close to the straight wall behaves a lot like it does for our circles. But near the apex, the system is now slowly relaxing. So the apex is doing some complicated stuff. We're working on this. Same with the velocities as well. All right. The next piece, before we talk about this, actually, I can come back here and say, okay, now we maybe are interested in this problem as well. When the jet has no confinement, so now we are interested in what happens beyond the aperture. It looks like it's thinning. So in fact, on the plot on the left, I'm plotting a bunch of these jet profiles. These are just averaged in time, so that's why the individual stragglers run away. What you can see, and this is an exaggerated scale, just to give you some idea, that the jet is definitely thinning. To give you some idea, if you go to a bathroom, a kitchen, open a faucet, fluids do this, right? Like as soon as they're falling with gravity, they're thinning, gravity's pulling them. Yeah. Why is a bunch of grains thinning?
Is the fluid's behavior dominating and it's behaving more like fluid at that moment?
But there's no surface.
It's the same with the water stream, right?
Don't you need the pressure difference to make?
Is it DM or?
True.
There is no air actually. So it,
DM.
this is experiments. This is experiment.
Okay.
Yep.
In the vacuum, do you see this?
I don't. I haven't done it yet. Although we should do vacuum in the lab. But no, DEM you definitely do. You see the thinning, and I think Heinrich Jäger's group has shown that you see the same thinning in vacuum as well. Say again?
Under Val's forces?
Yeah, but these grains here, these are the half mm grains. But the plot that I'm showing you up there is actually 1 millimeter big glass beads. So they're really big. There is no van der Waals of relevance here. The jet is still thinning. We think we have a little bit of a kinematic argument to explain why this jet is thinning.
Is it the initial trajectory from the orifice?
Yeah, so it turns out you don't actually need the trajectory necessarily, but as long as there's an orifice which is fixing the amount of flux in every slice, like that's the main constraint here. If you consider some kind of a self-similar coordinate, that's all you need to introduce thinning. Mainly right now we're talking about the z direction, is kind of where we've been focusing. In the z direction, the grains are essentially separating from each other because of gravity. This makes our life very easy because we don't have to worry about radial forces at all here. But as soon as we are interested in the thinning of a jet, you can see that now we are actually quite interested in some radial motion. Yeah?
It looks like it's trying to get to 55%. Right?
Yeah, always. Yeah.
Is that, yeah, that's the freezing volume fraction.
That's it. Yeah.
So my question for the DEM person, what is DEM?
Alex, here. Yeah, please ask him. I'm not the guy.
What happens when you change the coefficient of restitution? I asked this before. Do you still see thinning even with very, very high 99%?
Have we done a jet with
Yeah, I was going to say, so...
mass flux is okay.
For the mass flux, there wasn't that much of a change between...
But in the jet, we've not looked.
magnitude,
Yeah.
But we haven't done the full, 30 centimeter jet.
Okay.
Yeah.
I'll be very curious about it.
I'm sure it would change something.
If you guys, yeah, please.
Maybe following up with what Vijay was talking. So is the orifice, what is the shape of the orifice on like that?
It's flat.
Is it sharp?
But the grain comes like this, no? They want to make way into the orifice, so they
Yep.
already have
Yep.
lateral velocity.
Yeah, exactly. And that piece is necessary to define over what length the system will converge. And then at some point you can imagine individual collisions start dominating, and then you just get like a fixed width jet at that point. Yeah.
We do have radial velocity profiles at the orifice, for example.
There is definitely a small peak. I don't know if I have a drawing. No, I didn't make a drawing. But it's not at the center. It's a little off center, of course. But yeah, we do have some radial velocities. All right. I'll give you a nice video to just maybe give you a little bit more appetite of what happens in this third problem, where the system is now piling and spreading. Just to give you some idea here as well. You might think of this as being a silly, obvious problem, but hopefully the video will convince you that that's not the case. So initially, the jet hits a rough surface. You get a nice jump. That jump overall starts closing as grains are sedimenting in the system. And initially, you have a uniform spread of the pile. And then at some point, it starts breathing. No, they're not breathing. I'm kidding. So you're probably seeing some version of this already in that little hourglass in case it's still going around. No, it's not. Okay, but that's fine. You don't have to pass it again. It's okay.
The incoming stream also seems to like wobble a little bit, vibrate, yeah.
At the tip?
Just
in air? A little bit, yeah. You can't run away from this. It's about as minimum as it gets now.
What I'm trying to say is that time period related to...
It turns out it's not. It's not, yeah. So it turns out these avalanches, of course, you have some material that deposits close to the top. At some point, it starts spreading. As the material spreads, when it hits a new boundary, you will observe this. The grains essentially get stuck. I don't know why the resolution is so low. If you guys want, I can show it to you on my laptop. Whenever the grains reach the edge of this pile, they essentially stop spreading. Rigidity percolates backwards, and you introduce the next avalanche. So as the whole system grows bigger, at some point, those avalanches cannot span the entire system anymore, and they actually have to localize a little bit. We're working on this. If this is of interest to you, please, I'd love to talk some more here as well. All right, there's another system you've already seen where you have a rigid base and a free surface. And here are some examples of what actually happens in a rotating drum. I've just exposed them for a long time to give you some idea of the streaks. So the streaks are kind of telling you the system's frozen and close. I'm not going to take that long. And close to the surface, the grains are kind of free to flow. So that's where you have a strong decorrelation close to the surface, and then a lot of freezing as the system is kind of bound by the rest of the walls. Just to give you some idea, when the system is cohesionless, the free surface can cause lots of rearrangements in the system. As soon as you put in a little bit of stickiness, some cohesion comes here. Now the free surface behaves quite differently. The grains are not really free to move anymore. And actually what we observe is the system goes through periodic failures, and these failures will depend on how cohesive the system itself is. We're working on this. And just to kind of finish up with one last thing of another system where you have free surfaces and cohesion. So in this case, you have a column of grains, and that column is very rapidly lifted, so the system's allowed to spread. What you're looking at on the right-hand side are cohesion-less grains. You get a very small, very thin pile, very smooth on the surface. And you can observe as soon as you put a small amount of cohesion, here again, water is 0.5% by mass. You have some memory of the cylinder originally. That's kind of the broken up crown you're seeing at the center. And then beyond that, as the system spreads, it's essentially going through some cracks. We have some work on this as well. All right, that's a lot. I'm happy to take more questions. The big ideas we are pushing here just to kind of bring us back home. We know packing has to do something weird at rigid boundaries. Packing has to be kind of a minimum, go close to zero. There's as few contacts as possible at rigid boundaries. We also see, this is just an empty screen, all right? We also see that at free surfaces, grains actually have the most freedom to move. We think that this variation in how much grains are free to move and how blocked they are is actually much more core to these simple granular experiments than we believe. So one thing that I've not spoken about today is stress. And it turns out geometry is enough to explain a lot of what I just did today. So happy to talk some more, happy to talk about stresses. And if there's any questions, I'd love to take them. I should say I'm finishing my PhD this year. So if any of you are looking for postdocs, please let me know. Thank you. Any questions? So, I mean, like the weight, I guess, is a stress that we are measuring in mass flux. But the main organizing principle doesn't seem like you need much stress here. Just geometry is more or less enough. Yeah, is that enough? So we're building, of course, the linear algebra backbone of what this geometry does. Thanks to Alba, now we didn't talk at all about that today. But if you guys are interested in that stuff, I'd love to talk some more as well. I know I've shown Teja some of it, and it's been spent around a little bit. Yeah, okay, thank you. Thanks for your time.